Okay, so in this video what I'd like to cover is going to be the first part of chapter 17 within the PowerPoint, and this is module 6, additional aspects of chemical equilibrium. Specifically talking about the common ion effect and what is a buffer. So how to, definition and how to make one. Okay, and I'm going to also be following along with the in-class worksheet as well as the PowerPoint. So on the slide on the PowerPoint that talks about the effect of acetate on acetic acid equilibrium, when we're talking common ion effect in an acid-base equilibrium system, we are talking about what happens if we add something that is already in solution based on the equilibrium expression, and how will that impact the equilibrium? Will it shift left, right? Will it have no impact? So let's take a quick look at acetic acid. And remember, it can be written multiple different ways, but acetic acid in this case is written as such. And in water, we end up with an equilibrium that gives us acetate ion and H3O plus, right? And this equilibrium expression is described by KEQ or Ka specifically, which is H3O plus CH3COO minus all over acetic acid, right? We should be able to write the Ka for any of these expressions at this point. This is extremely imperative, right? Okay, so if we assume that this system has reached equilibrium, then we assume that we should have a little bit of each of these, right? And the magnitude of each of these is directly a function of Ka, and that is a function of the acid itself, right? Now, when we talk about Le Chatelier's principle, up until this point, we've talked about it for equilibrium systems that were not acid-based, but the same concept applies. We can put do something to the system on either side, and that will impact the direction that it will go. So, in one instance, right, they are talking about in the PowerPoint is that if we added acetate, let's say we added sodium acetate, which would be, let's say, a solid, and we added it, then it dissolved to form sodium ion in solution and acetate ion in solution. What have we done? Effectively, we have added and increased the concentration of CH3COOH, and from a ice perspective, right, from an ice perspective, we have added to the initial of a product already. And what that is going to do is that's going to force our equilibrium left. So hopefully we should be comfortable in knowing that the addition of this is going to force our equilibrium left. Which means that we are going to increase the concentration of the acid, decrease the concentration of the acetate, and thereby increasing this will also decrease the concentration of H3O plus, thereby increasing the pH, right? So we are forcing the equilibrium left, right? We've added acetate, but acetate will decrease as equilibrium is reestablished. Acid will increase. We therefore have to decrease products, which will be a decrease in acid hydronium ion, and therefore an increase in pH, right? So the addition of a common ion will shift the equilibrium away from the side of the reaction where you added the common ion. So in the examples that I gave you on the in-class worksheet, I gave you some examples of potassium cyanate and cyanic acid. So, if we look at cyanic acid and water, we see that it is going to be in equilibrium with cyanate ion, anion, and hydronium. So this is the chemical equilibrium. We are saying in the problem that we are going to be adding KCNO, potassium cyanate, and therefore this is going to dissociate in solution to form a common ion, which is the conjugate base. Remember, we still need to make sure that we can write that. Acid, base, conjugate acid. So we have added a common ion, which is going to shift the reaction left to reestablish equilibrium. Which is going to increase HCNO. It's going to decrease H3O plus and thereby increase pH. And what I have left, shift the reaction left to increase the pH of the solution. Okay. The other example in the in-class worksheet is magnesium fluoride HCl. Okay, so if we're looking at HCl plus water, we know that we're going to have chloride ion and hydronium. Now, what do we know about HCl? We should be able to recognize immediately that it's a strong acid. What does that mean? That means that it dissociates completely. What does that mean? It means that we do not have an equilibrium system here. We are dealing with pretty much a full reaction only. Why? The conjugate base is neutral, right? So the addition of MgCl2 will dissociate into Mg2 plus 2Cl minus, but it has no impact. So it will not shift the reaction or change the pH, because chloride ion and magnesium, if we remember, are neutral in solution. The pH is a direct function of the concentration of a strong acid. So this is not a situation where the common ion effect applies, and you need to be able to recognize that. Now, they also give an example, and I don't have this on the workout, the in-class worksheet, but the common ion also works for weak bases. If we took a look at ammonia, and water to create ammonia and hydroxide, if we were to add ammonium iodide, then that would dissociate into ammonia plus iodide ion. And this is, in fact, a common ion. Remember, we have a base, an acid, a conjugate base. We are adding a product of the equilibrium, so we will shift left again, which will increase NH3. It will decrease OH minus and thereby decrease pH. Right? So here is a situation where you can do the exact same common ion using a basic system, increasing your reactants, decreasing one of your products that impacts pH, and thereby decreasing pH, making it less basic. So you can do that not only with acids. I wanted to show a base example. Okay. Now let's talk about buffer. What is a buffer? Okay, from a practical aspect, the majority of the large-scale chemistry that is being done on an industrial standpoint is going to be utilizing aqueous buffer systems. Blood internally is a buffer system that is extremely complex, but the purpose of a buffer is to be able to withstand changes in pH if you add something to the system. So, by definition, a buffer is a solution with a acid conjugate base pair or a base conjugate acid pair common ions. Very similar to what we just talked about. So this is segueing us into buffers. They can resist changes in pH because we have both an acid plus a base in solution. Right? So we can take acid, take base in the solution, and we have an acid and base both to react with that. Okay. Most of the time, they have concentrations that are greater than 1 times 10 to the negative 3 mole. So anything lower than that is not effectively a buffer because it cannot withstand very much change because it's such a low concentration. And also a key is that both acid conjugate base concentrations are approximately the same. Right? So they're both the same. And when they're both the same is when we have the buffer that gives us the best practical use, right? Is the best to use. Now, there are 2 ways to make a buffer, right? There are 2 ways to make a buffer. And the 2 ways to make them, and we have problems associated with both of these, but the 2 ways to make them is to mix the acid with the conjugate base or base with conjugate acid in solution. For example, let's say we mixed HF and NaF. Okay? HF and NaF. We have not only the acid, weak acid, but we have its conjugate base F-. Remember, the sodium ion in solution is neutral. It is just a spectator, as we say. Or you can use acid and convert some into A-, and I guess I should be using HA here, but you can convert some into A- using a strong base. So in the case of, let's say, HNO2 plus NaOH, we create some of the NO2- plus water. And therefore we have made our base conjugate acid base pair in solution. So we can do it one of two ways. What we first need to be able to do, and there's some problems on the computational side, but we need to be able to recognize which ones are and which ones are not. So let's take a look at our in-class worksheet and let's look at each of these. So the first one, HNO3, NaNO3. As soon as we look at this, we need to be able to recognize each of these. Now, HNO3 is a strong acid. Immediately, that means that we are not dealing with a buffer, because there is no equilibrium that exists with a strong acid. So we can go ahead and throw that one out. All right, calcium hydroxide and water. Immediately, we should recognize calcium hydroxide as a strong base. Therefore, no buffer. We can't utilize that as a buffer because it has no equilibrium. Now, HCN, or hydrocyanic acid, and lithium cyanide. Now we are dealing with a weak acid and its conjugate base, cyanide, so we are dealing with a buffer. have the weak acid conjugate base pair. Next, we're looking at ammonia and ammonium iodide. We just talked about this one. We got a weak base and its conjugate acid. So yes, again, we are dealing with a buffer. Next one, acid and cesium. We can go to our reference material if we don't recognize this to get the nomenclature, but this is in fact a weak acid with its conjugate base. So we are also dealing with a buffer. So lastly, we're dealing with HF and NF3. HF is in fact a weak acid. NF3, a lot of people are going to get confused on this example because NF3 is a compound. It is also a base, right? We can have it as a Lewis base by definition, but this is not the conjugate base pair of HF, right? The conjugate base pair of HF is F minus. So this could be a solution, but it is not a buffer. So those are a couple examples of being able to recognize them, being able to determine if it is a buffer system or not. You should also be able to determine, and we're going to see this in the calculations, how you can decide whether this buffer is going to have an acidic or basic pH, which is a function of pKa. So buffers give us the ability to, again, neutralize small amounts of acids and bases. But now let's talk about some of the mathematics of a buffer in computation. So here is the derivation that's done in the textbook. You don't necessarily have to know this derivation, but this formula that we're going to get to is in your reference material. So if we know that Ka is equal to A minus plus H3O plus all over HA, and we know that if we then rearrange, we know that H3O plus is equal to Ka times HA all over A minus. And we know that pH is equal to negative log of H3O plus, which is equal to negative log of Ka times HA over A minus. We can rearrange this expression using our idea of pH and pKa. So technically, we now have pH is equal to pKa plus negative log of HA over A minus. And to simplify this with rules of logs, we can take the inverse of this fraction and change the minus so that we end up with pH is equal to pKa plus log of A minus over HA. And now we have what is known in your text and on your reference material that you have as the Henderson-Hasselbalch equation, right? Henderson-Hasselbalch equation. And this is what is going to be used to determine and calculate the pH of a buffer, the pH of a buffer. As long as you have information about the acid and the conjugate base. This same thing goes for POH is equal to PKB plus log of HB plus over B. And this is also in your reference material. You just need to know how to use each of them. As long as we know the relationship between pH and POH, this should be fine. Now, being able to calculate the, and this goes back to a question on number 4 on the in-class worksheet, being able to use Henderson-Hasselbalch, there's one thing that makes this simple, is that if the concentration of A minus is equal to the concentration of HA, then A minus over HA is equal to 1. And if A over HA is equal to 1, then the log of 1 is equal to 0. And therefore, pH equals pKa. And this is important. The reason it's important is because when pH equals pKa, and both of these concentrations are equal, when we've made a buffer of equal concentration, it makes a very quick calculation to determine what the pH of the buffer should be. And that is going to be something that you're going to use moving forward when you're thinking about, especially on the, I think in the problem set, there's a couple examples of how to make a buffer and what should the pH be. To give you a general area that the pH will be in if it was a 1-to-1 concentration ratio, then it will be pH is equal to pK, or negative log of the Ka, again from the reference material. Okay, so now let's look at questions 5 and 6, and we'll finish with those for this portion of the video. How to calculate the pH of the buffer, and we've made the pH buffer 2 different ways. Okay, in the first example, we have HNO2 and strontium nitrite. Realize that there is an error on the upload, and I'm going to change that. If you have the early version, it should be SrNO2. So they say we have 77.3 grams of nitrous acid, and we have 201.6 grams of Sr, and this should be NO2. We should have 2 moles of each of these. Of each nitrate. All right, now, do we have a buffer? Yes. Yes, we have an acid-base pair of HNO2 and NO2 minus, right? This is a weak acid. It is on our reference material. We do have a Ka. So all we need to be able to do at this point is to be able to calculate the concentrations of each of these in 5 liters of DI water. So we got volume total is equal to 5.00 liters. Okay, this is general chemistry 1. Convert to moles, divide by 5 liters. So 77.3 grams, 1 mole of HNO2 is equal to 47.02 grams, and we have a number of moles is equal to 1.64 over 5 liters, and we have a concentration of HNO3 is HNO2, excuse me, is equal to 0.328. Okay, now strontium nitrite, 201.6 grams, 1 mole of strontium nitrite is 179.64. That's equal to 1.12 moles of SrNO2, but we need to know that for every 1 mole of SrNO2, there are 2 moles of NO2 minus, which is what we're interested in, and that is equal to 2.24 moles of NO2 minus divided by 5 liters gives us the concentration of NO2 minus, which is equal to 0.448 mole. All right, so again, the straightforward stoichiometric calculation, general chemistry 1. Now, once we have those 2 pieces of information, we know that pH is equal to pKa plus log of concentration of the conjugate over the weak acid in this case. If we go to our reference materials, we find our pKa is equal to 4.5 times 10 to the negative 4. Sorry, our Ka, 4.5 times 10 to the negative 4 plus log, and then we have our 2 concentrations. In this case, this is A minus, and this is HA. Shouldn't be any confusion there. Shouldn't be any confusion. And therefore, we have 0.448 moles over 0.328 moles. And once you plug this in the calculator, you end up with a pH equal to 3.48. Now, we have non-equal amounts. We actually have a little bit more NO2 than we have acid, but due to the Ka, this is a weak acid, but it is fairly strong, right, due to that value. So we should expect this still to be acidic, and we have created a buffer of around 3.5 pH. So this is the first example of adding in the acid and its conjugate to make a buffer. Okay. Now, in the second example, or question number 6, I've asked you to calculate the pH using an acid and then neutralizing some of that acid with a base. Okay, so we have 150 milliliters of 0.285 molar HF. So we got 0.150 liters of 0.285 moles of HF per 1 liter. That gives us moles of acid, and we have 4.275 times 10 to the negative 2 moles. And that is then, we've added our base, 0.70 grams, and if we show 1 mole of NaOH is equal to 40.01 grams, we end up with 1.7 times 10 to the negative 2 moles of OH minus. So we got moles of acid, moles of OH minus. Now we should take it into consideration that we're dealing with a neutralization. So this is where we need to look and understand and talk about moles. Okay, so if we're talking about moles, I would suggest that you write the neutralization out. You write the before, the limiting reagent, and the after. So we got HF plus OH minus gives us H2O and F minus. All right, before we're dealing with 4.275 times 10 to the negative 2. Here we have 1.7 times 10 to the negative 2. We're not worried about water because it doesn't exist in the Ka expression, and we don't have any fluoride to begin with. Well, our limiting reagent is OH, so we minus 1.7 times 10 to the negative 2, minus 1.7 times 10 to the negative 2, and that leaves us with 2.575 times 10 to the negative 2, no hydroxide left, and 1.7 times 10 to the negative 2 F minus. All right, so now we know the number of moles of the two components. We use the base, strong base, to neutralize some of the acid, to create the conjugate base, and now we have effectively a buffer. To calculate the pH, we need to plug in these values into Henderson Hasselbalch after we make them concentrations. So, to make them concentrations, we have to divide these number of moles by the total volume. So, the concentration of HF is equal to 2.575 times 10 to the negative 2 moles, all over the total volume, 0.15 liters, and that is equal to 0.172 molar, and then the conjugate is equal to 1.7 times 10 to the negative 2 over 0.15 liters, and that is equal to 0.113 molar. So, now that we have the two concentrations, we can go to pH is equal to pKa plus log of A minus over HA. If we go look for the Ka value here, we see that the Ka value is 6.8 times 10 to the negative 4. So pH equals negative log of 6.8 times 10 to the negative 4 plus log of 0.113 molar all over 0.172 molar. And now we end up with a pH of 2.99. So also an acidic pH. Notice that these two values are fairly close to one another, 0.113 and 0.172. So we should expect this to be an acidic buffer because we're using a weak acid. So this is the second way in which to create a buffer using two different methods. Now, the buffer and the way we use Henderson Hasselbalch has been shown to you here, pH, pKa. And then I'm going to do some examples of Workout Wednesday of using bases. Now let's talk a little bit about the buffering capacity. So if we were to take a look at a buffer that was pH equal to negative log 6.8 times 10 to the negative 4 plus log of 0.00113 over 0.00172, what we should recognize, right, is that the ratio here has not changed. I've just made this a more dilute buffer. Let's say I just added a bunch more deionized water. The pH here will be the same because that ratio and that logarithm is going to be the same. But what will not be the same is buffering capacity, right? This buffer here has a higher capacity because it has higher concentration. So because we have a higher concentration, we have a higher capacity. From a practical standpoint, in a laboratory, experimentally, we want to be using the buffer with a capacity that is reasonable. These buffers, again, like they said, 1 times 10 to the negative 3, which is what these are, is about as dilute of a buffer that can be used reasonably. So we have a higher capacity here, so the amount of acid or base, you need to be able to recognize, looking at two different systems, which one should have the higher buffering capacity. And in this case, it's going to be the first one because of the higher concentration. Now, one thing that you don't want in a buffer, in this case, and in any case, is you do not want these two values to be more than 10 times different from one another, because then that does not give you an effective buffer. So you can make what we call a bad buffer, or a buffer that is not necessarily going to work well. And that has to do with capacity and the ratios. Now, when you add something to a buffer, obviously you're going to be adding and subtracting from the acid or the conjugate base in this case, and that is going to allow you to calculate the new pH of the buffer after you have added something, because you are going to be changing these values. As long as you're dealing with a strong acid, strong base, then you know you're going to have complete dissociation. So we'll do some examples of those in the Workout Wednesday as well, but I just wanted to show these as a basic example. All right.